In 1801, Thomas Young performed the experiment which provided the first solid evidence for the wave theory of light. He created a narrow beam by letting a light source shine through a slit S, then let it fall on a screen with two slits A and B close together, and finally let it shine on a second screen, S prime. It happens that this classic double-slit experiment, along with some variations, demonstrates all the fundamental concepts in quantum theory and shows how they relate to each other. The double-slit experiment can be performed with either a light beam or a beam of electrons. The particular apparatus involved will be different, but in either case, the results will be the same. In the broadest terms, the experiment consists of a source, a double slit, and a screen or target with an appropriate detector. Now, we can perform a similar experiment with marbles or BBs or bullets, in which case the slits become gaps in a barrier. We can graph the number of particles hitting any particular spot, first using one gap only, then the other, then both. The key point here is that the graph that results from using the double gap is exactly what we would expect if we simply added together the graphs that resulted from using each gap separately. If we perform a similar experiment using waves and barriers, in a ripple tank say, we can graph the intensity or energy content of the wave as a function of its amplitude. We simply measure the height of the waves against the rear of the tank. Once again, we can construct a graph using first one gap, then the other, then both. This time, the graph resulting from the double gap is quite different, the result of the waves interfering with each other rather than simply adding together. Now, in the double-slit experiment, using, remember, either light or electrons, the result, with both slits open, is an interference pattern. If only one slit is open, the interference pattern disappears. That is, the result is exactly the same as with water waves, and it was, of course, exactly this sort of result which, in the case of light, led to the conclusion that it was a wave. The reasoning is almost absurdly simple. In the double-slit experiment, waves produce an interference pattern. Particles do not. Light produces an interference pattern. Therefore, light is a wave. It happens, however, that there is another difference between the way particles behave in this experiment and the way waves behave. In the case of marbles, BBs, or bullets, it is quite clear that they come in lumps. They arrive one at a time, each one the same size, each one arriving at some particular spot on the target detector. Waves clearly do not do that. A water wave can be any height at all. Moreover, the height or amplitude of the wave is really a measure of the energy contained in the wave. That energy is spread out over the entire wave front, rather than being concentrated in one lump. The second difference, then, is that particles come in lumps. Waves do not come in lumps. Both light and electrons come in lumps. For convenience, from this point on, we will only refer to electrons. But remember that all of the following applies to light as well. Consider what happens in the double-slit experiment when we use a very weak source and an appropriate detector. The source can be made so weak that the electrons arrive one at a time. They come in lumps, each arriving at one particular spot on the detector. This complicates matters, for the first experiment shows that electrons behave like waves in forming an interference pattern. But this modification shows that they behave like particles in that they come in lumps. And there is more. When the source is so weak that the electrons come one at a time, something very interesting happens. At first, they will seem to be distributed randomly. But as more and more impact points accumulate, it becomes more and more obvious that an interference pattern is forming. That is, in the case of the electron, even when there is a long time between each impact on the detector, the interference pattern still appears. Now, in the case of water waves, an interference pattern is produced either by 2 point sources which are interfering with each other, or by one wave which has in effect been split in two to create the equivalent of 2 point sources which interfere with each other. The question comes up, what is the electron interfering with? One unsatisfying choice is to think of the electrons as particles which somehow know how to guide themselves to form an interference pattern. Another choice, equally unsatisfying, is to think of the electrons as waves which somehow contract to a point on impact. Could it be that each electron somehow goes through the slits as a wave and then interferes with itself? Or could each electron somehow split in two, each part going through one slit and then interfering with itself that way? We can try to find out. If detectors are placed at each slit, each electron can be tagged as having gone through one slit or the other. We find that the electron registers as a particle at the slit and on the screen. That is, with a detector placed at each slit, we can determine that the electron goes through one slit or the other as a particle, and that it arrives at the final or target detector as a particle. But something very odd happens. The question is, if it goes through the slit as a particle and arrives at the screen as a particle, how does it produce an interference pattern? The answer is, it doesn't. The interference pattern disappears. In fact, the graph of the impact points is exactly what we would expect if we were dealing with tiny BBs or marbles. It is the sum of the impact points which result from using each slit separately. But how is it, why is it, that in one circumstance an interference pattern forms and in another circumstance it doesn't? Does this make any sense at all? Yes. Consider the wave aspect of the situation first. If there is no detector at the slits, the de Broglie wave passes through both slits. Each slit acts as a point source for the de Broglie waves, which spread out or diffract to finally interfere with each other at the target detector. But the situation changes if we place detectors at the slits. For in detecting the electron at one slit or the other, we have confined the wave packet to the one slit. That slit will then act as a single point source for the de Broglie wave. Once again, the de Broglie wave will diffract as it moves towards the target detectors, but this time there will be no other wave for it to interfere with. Now, what if we choose to think of the electron as a particle? In order to know which slit it is passing through, we have to detect it. And in order to detect it, we have to poke it with something. A photon, another electron, an atom, something. That poking must necessarily give the electron a little kick and change the results of the experiment. But this logic is the same as for the Heisenberg uncertainty principle. In fact, it turns out that it is the Heisenberg uncertainty principle. We are then led to a more subtle concept of wave-particle duality. Wave-particle duality and the Heisenberg uncertainty principle are, in fact, different aspects of the same underlying reality. It is not enough to visualize an electron as a particle with a wave aspect or as a wave with a particle aspect. What we are forced to do, finally, is to give up the attempt to visualize it altogether, an attempt which is guaranteed to lead to confusion, and simply accept the fact that they behave like a wave in certain ways and like a particle in others. It may well be that nobody understands quantum mechanics, but that is the way the universe behaves nonetheless.